So basically, as Nida said before, storage devices so far have been capable of doing just read, write, and erase. That's basically it. And then a little bit of management, and with smart and stuff, you can see how the drive is doing, the health, etc. So what basically the trend has been, and then this is actually not just us, but folks like Microsoft have been working on this type of idea, also Samsung, in trying to bring more computational resources closer to where the data is, or where the data goes through. So we're seeing the same type of stuff, software-defined NICs, etc., where you can add processing capability in the NIC itself, and so on. So coupled with that, there is more and more traction in the field of heterogeneous computing. So coupling, distributed processing with heterogeneous computing, GPU, FPGA, and so on. So this is a trend. It's a very hard problem to solve. It took NVIDIA a lot of time to get through that. And from the concept of computing with a GPU to CUDA, it took many, many, many years, right? But I think we're going to go over the same type of path here. So what we're saying is that, hey, there's stuff that we can do also in the storage. So whether or not we're doing the right thing or in the right direction, it's up to our customers to judge. But I think that definitely there's a lot we can do by bringing computation closer to where the data resides. So and moving computation to data is cheaper than moving data. So that has been the trend, and we haven't invented this. So the folks that developed MapReduce, for example, at Yahoo and Google, they've actually implemented that. And the concept of in-situ processing, in-situ is a Latin word, we didn't invent that as well. It's do the computation where the data is a concept that exists, has implemented in MapReduce and Hadoop very effectively. And what we think is that by providing a certain infrastructure that can give you access to the data very quickly without moving data, can solve some problems efficiently. Absolutely not all of them. We're not here to replace CPUs, replace GPUs. That's not what we're claiming. We're here to help and augment the capability of existing systems, right? So I have a couple of slides there. So at a very high level, how it works, so to make sure that we're all on the same page. So how do we do computation today? So I'm showing here a very simple example of what a server is with its host CPU with many cores, DRAM, and one or more storage devices, right? In this case, I'm showing an SSD. I'm not going to show a rotating media, of course, with the flash media inside the device, right? So basically, at some point, somebody decides to store information inside the storage device. So there's no computation that happens without the data being stored somewhere first. Now, once you decide to compute, you have first to read from the storage device. That information goes and stays in DRAM, and you perform computation. So these steps may have to happen multiple times if you're processing a very, very large amount of data that's larger than the CPU, the DRAM size, for example, right? So we're talking big data sets. That's the case. Now, finally, at some point, you've done your computation, and your application, receives the results and does something with it, transfers it somewhere else, or decides to, take action doing some more computation. Now, how would in-situ processing work? So, in this case, I still have my system with a CPU and a DRAM. I could also have accelerators like a GPU or something on the system. I'm just simplifying here. And what I have in my storage device is now that I have the capability of processing data. So Nader already said that this in-situ processing box, in this case right now for our first implementation, is a quad-core processor from ARM, right? So we went to a 64-bit application processor that can give us, the computing capability of any modern processor. So what happens once you've written to the storage, to the media, what you're going to do is move the data that you need from the media to internal buffers, and then perform the computation internally, right? So it's the same thing that happens. So these steps may be repeated multiple times because obviously we're under the assumption that we're processing, big data sets. And once you're done, you can push that result up in the food chain so that eventually the application that's running on the CPU can consume that result. Now you can imagine that since a system may have multiple storage devices, then these can work in parallel, right? And the same computation or a different computation could be happening in parallel in all these storage devices that are connected to this CPU. And the application there could be orchestrated. And we're going to show an example, or more than one example, where we're doing exactly that, right? We're actually implementing a distributed processing system where things are happening in parallel. And then obviously, at some point, the application can make use of the results that are obtained in each individual storage device, and then provide its own, perform its own computation as well. So you can see that for those who are familiar with MapReduce, this is a very much similar concept, right? Where you're basically offloading some sort of part of the computation that you need to perform to the storage devices that are much closer to the data where they're residing. Questions so far?
Yeah, I have two questions.
Sure.
So one is about the fact that most of these computers, okay, consider that you are not going to process invoices with SAP, okay?
No.
Probably. Okay. So most of the computers have specific CPU, GPUs or FPGAs, okay, while you only have 4 ARM CPUs. Mm-hmm. Isn't it a little bit,
Sure.
too little of a CPU to make all of this?
Yeah, so you have a point. And so first of all, this is a design point decision. So we're a startup, we have one first design out, right? You could imagine that we could have a second design out with infinite resources very shortly with a lot more processors, beefier CPUs, and even embedded GPUs, right? So the design point doesn't really go against the concept itself. But I get your point, that's true. When we see the benefit in some, much more modern architectures that are being deployed in data centers where, like for example, recently Facebook and Microsoft Azure proposed, an open server architecture with 64 SSDs, right? So in these concepts, with 64 times 4 ARMs, you can do the math yourself.
Yeah.
The number of MIPS you get is way more than a Xeon especially from some sort of application. So you're absolutely right. And we show some examples, of actual computation that we have performed, where we show that we do not help the CPU at all with a small number of drives. And as you scale up, then you start helping significantly, the computation done in the CPU.
How much
you're
buffer?
right.
Go ahead. How much buffer?
Yeah, so we do have internal buffers that are in the order of megabytes only. And we also can use our DDR, which in this first design point, as I mentioned, is up to 8 gigabytes of data. So, and obviously, the in-situ processing subsystem can use the flash as its own private storage. So imagine that you have now, for example, several terabytes of storage in one of the drives. You can reserve, a few gigabytes or a few dozens of gigabytes just for the in-situ processing system. So you'd end up with the ability of, doing like, swapping, memory swapping, etc., with a much larger amount of data.
So what's the flash to ARM processor memory bandwidth compared to accessing it from the Xeon over the PCIe bus?
So the ARM is in a way much closer to
I'm assuming
the back end, right? So we're basically getting I think it's a little better bandwidth than what the Xeon can get.
Just a little better.
Just a little better.
Okay.
Because it ends up being a function of the bottleneck being the error correction code, error correction IP that we use, LDPC, etc. Those are going to reduce your bandwidth and minimize the stuff. So it's better, but not significantly better.
Okay.
But also to add to that, in general, at least in the first implementation we have implemented, the access to the flash, it is orders of at least 4x of the host interface.
Oh, okay. So that's
So-
not 4x isn't a little.
Right. Well, it's two parts. One is accessing to the data, and then as it goes out to the host CPU, just like you saw on the other one.
Right.
The other part is the CPU portion of it. So in general, access to the data is a lot more inside of the drive compared to the interface that goes to the host CPU.
Right.
Yeah, but- yeah.
And in a model like
Yeah. So
and in a model that's got more than a handful
Then it makes
Exactly.
a big difference.
Well, in a model that's got more than a handful of SSDs, you're going to have PCIe lane contention as well, because
Exactly.
there's going to be a
that's
switch
when that
between the SSDs and the processors.
yeah, and that's
So-
when that
Right.
We can't do all that much in each device, but the parallelism adds up fast.
Yeah.
That's right.
I realize I might be going way too far out, but a couple things you said just kind of made my head explode. Long term, are you guys thinking that, hey, we got this core design, we can scale up these components? And I totally get, I think that's a good idea. I understand this point of having kind of a hard market, but in the future, have you considered like adding, things that are more auxiliary, like for example, in-flight and staged at-rest encryption?
yes, absolutely. I'm going to touch.
Yes. Absolutely.
Do you mind if
Very
we
good.
Please.
No, it's just
Very
I
good.
can address it, but maybe
No. If you go ahead, please. I'm happy to wait.
yes, and actually it's a great point.
Right.
Actually,
Yeah, you can jump. Just
No,
to
no, no,
add
fine.
to that, so the in-situ starts as the basis to be a dedicated CPU, but there are auxiliary hardware acceleration. One of them, it's what you just described, but there are additional one that is already implemented and is planned for some additional one to be added.
All right, cool. Very cool.
So I'm a computer architect. So, but with time, I learned how to be a little bit more humble, and that what I learned is that you can do the fanciest architecture you want. If you cannot program it, nobody will use it, right? So there's a lot of examples of that in many cemeteries across the United States in the world. So one of our first focus is to provide a seamless programming model, and hopefully I can convince you guys that we have that. So obviously the other thing that, as we talked, we need to help our customers manage capacity growth, and that's an angle that has nothing to do with in-situ processing, is the fact that we're providing extremely high capacity drives for those who want and need, right? And then the third thing is that in-situ processing has to help you, at least in some use cases, scale, right? Scaling is very important. So these are not the only focuses, but these three are extremely important, and I want to highlight those, and especially the programming model, right? I've worked before in super cool architectures that never have seen the light of the day because of that.
And you guys are pretty confident that you can do that? So I mean,
Absolutely, yeah.
I mean, no disrespect, but from my experience, well, you just described the seamless. That is actually the hardest part of this whole thing. I mean, it's like because there's
You're
such a human element to it,
You're
right?
absolutely
I mean, it's
right.
like that's not easy.
Yeah, you're absolutely right. So before we go any further, so I just want to just say a few more words in that same direction on some of the most important dimensions that will enable computational storage. I'm not just talking just about us. One is the operating system. You have to be able to run an operating system. It's crazy to think that you can do just hardware acceleration and resolve problems because it's too much customization. Nobody has the time to be doing it all over again and customizing for every new application, every new use case. So going from what bare metal or RTOS is to, in our case, we decided to jump to 64-bit OS right off the bat, right? But we think this is very important, and it's just an opinion.
RTOS is interesting though.
Yeah.
I mean, there could be other. And RTOS is interesting. I mean, there's some interesting other angles to it. I mean,
Sure, yeah, but RTOSes are being used for SSD management,
Yeah.
right? And we don't take, but
Yep.
when you're running user application, no programmer wants to run on an RTOS.
No.
On the hardware side, so
Too bad, too.
Other researchers and researchers within companies or in the academia have tried to do things similar to what we have done, using the processors that they had at hand and so on, which today is in most cases the processors that are used for implementing SSD management are 32-bit real-time processors, the likes of ARM, MX, M7, etc.
It's building up.
What we think is that we gotta push for more hardware acceleration, for example, encryption, obviously, and a lot of SSD controllers already have some of that. But application processors, and in our case here, I'm highlighting that we pushed to 64-bit application processor. There was no gain in staying at a 32-bit for any reason. And user application, obviously, SSD, programmers have been writing for a long time and so on, but we want to help users run their own applications, so writing application software, so this is all to help them. And then what we think is very important to give some virtualization support, and we've opted for containers, which is a very lightweight technology, and enabling AI applications, right? These are becoming more and more common, and AI needs a lot of data, and we are very close to data, so we think there is an opportunity there. With in the future, adding AI acceleration within the drive itself. There's nothing that prevents us from doing that. We're actually working on it right now. So this slide basically kind of summarizes what we've discussed in the past 2-3 slides. So what today's SSDs are giving you a lot of performance. We haven't focused on that. We're not providing 1 million IOPS to our customers. And maybe Scott and Neither can elaborate more on that later. A lot of our customers are not looking for the fastest CPU, the fastest SSD, the lowest latency, etc., because they are aggregating a lot of SSDs, they're aggregating performance, they're aggregating everything. So what we need to do is add resources inside the SSD, the processor I talked about, hardware acceleration. Also, go for 64-bit application processors that allow you to support an OS. So we run Linux inside, and virtualization in the form of containers. That's where you get the smart SSD that we're putting out. So, so how did we do this? So we had to design our own controller, obviously, because there was no controller out there in the market, off-the-shelf controller that would have all the features that we need for this kind of design. So we are proud to say that we are the first sub-28 nanometer SSD controller out there. So that helps us integrating all these computing resources, the processors, as well as lowering the power, which is a main concern especially for data centers. We're using ARM processors, hardware acceleration. I'm going to elaborate on the hardware acceleration a little bit more later. So especially encryption engines and regular expression acceleration engines for search inside the drive. And we run Ubuntu so far, but we've done a lot. We played a lot with the Octo to implement our own flavor of our own internal distribution to experiment with, and we support now Docker, and we're looking at other containers like Resin.io, which provide maybe like better support for edge type applications than Docker. So this is the foundation, right? With that, we build an SSD. Obviously, we're focusing a lot on in-situ processing. Just remember, we have an enterprise class SSD controller as a foundation. So this is what we've been doing for a few years in the company, is building that foundation first and then in-situ processing on top of that. Also, something I want to remember, I don't know if we have a slide about that, but we currently have 14 2014. 20 patents granted that covered aspects of SSD management that are new, error correction code, as well as in-situ processing. So,
The question.
yes.
If at some point it's appropriate, I would just love to hear just like 1 minute of like, how nasty was it going to 14? I mean, was it a burden on you guys, or was it mainly on the foundry? Like, what was the experience?
No,
Step up.
well,
Yeah,
actually, there are many scars. So
That's what I was hoping.
there is absolutely a lot of challenges going. Every geometry as they go, even though the process is mature, the design flows still is challenging. Still, it's in the first, I don't know, 50 or so designs.
Yeah.
So and that took a toll on us for sure, financially as well as the time-wise. But it was absolutely necessary. So as Vladimir mentioned, just as a standalone SSD, it has some fundamentals in it to address what the data centers are looking for. So it's an enterprise class, but it's not about the IOPS, because all the data center guys, they said we have plenty of IOPS. We don't actually know what to do with the IOPS. We bring it down. What we are looking for, we need a large capacity, but the main focus for us, other than watt per terabyte, it's the latency and not latency of write. It's latency of the read, and we don't want it the fastest latency, shortest latency. We need a latency with a consistency. They are looking for the 5 nines to be consistent, and that's what we are providing as a basic fundamental of the SSD. Then in addition to that, it's the in-situ that makes a difference. So going to the 14 nanometer, it gives us the additional edge for the watt per terabyte. So all the controller exists in the world for the NVMe, because everybody goes and tries the high IOPS. They are power hungry. They all are like the old Cadillacs, which are wonderful. They all have 12 cylinders and they are great. However, majority of the market is looking for the electric car that's efficient to do certain things. And that's what we are focusing on.
That was awesome. And that's awesome. 14 nanometers. Very
so if a car analogy, I would say there's a lot of Bugatti Veyrons out there with Tesla.
Careful. I don't know. It's going to be a test.
I think there's 7 Bugatti Veyrons, actually.
yeah.
So, yes.
That's cool.
And presenting this, our technology, is also always a little bit challenging because there's a lot of interest in the in-situ processing side, and we kind of veer away from talking about the fundamentals that are, the SSD, the management itself, the flash, etc. What wattage we get. So questions are welcome, and we can, go back and forth.
Get there.
So I just want to say a few more words about the ecosystem. So in terms of development tools, besides our software design kit that we have already right now, we have used a lot Yocto, and it's a extremely interesting tool that we fully support to build your own flavor of operating system, and that's for more educated customers. Some of them might want to do that, but we've settled on Ubuntu for our vanilla flavor, and we support 1604 and Ubuntu Core. Now, more complicated file system and communication protocols. So there are many ways to go about how we manage the information that's stored in flash and how we coherently manage the access from the in-situ processor system and the host to the same data. So we have already implemented GFS2 and OSS2 as examples of distributed and clustered file systems, and it runs very smoothly. We also have a lot of applications that we're running in-house using MPI for the support to parallel and distributed systems, right? And it runs very smoothly. In terms of container and so we support lightweight virtualization with Docker, and we're gonna show an example. But we're also very interested in more container technologies, and just highlighting resin. It's a very, very interesting technology. We're going to explore more.
And then I know if you said how many customers or betas you're doing at this point, I didn't hear. I apologize. But do you have anyone testing any of any of those file systems for the MPI functionality outside of your own labs? I mean, are there any like HPC type customers that are kicking the tires?
No HPC customers, but Microsoft Research is working with us on using MPI.
All right.
And we're actually running experiments with them using OCFS2. But to be honest, it's in our labs. But we're working together on the same experiment, so we're running both.
Far out.
So we got GFS. GFS didn't work. GFS2 kind of works okay. OCFS2 is so much better than, we still mention GFS, but
a lot of that stuff is a labor of love.
All the developers, they just forgot about GFS. OCFS is so much better.
So you're talking about running a distributed file system across the SSDs themselves?
Yep.
And
but
my brain hurts for a second.
This is very exciting.
It uses choice, so you don't have to. There's more simple mechanical ways. So if you're doing like extremely long processing, right? So you can set up a session just using mount and unmount, and then fire off, and that's it. And if you're running for hours, who cares, right?
Right.
The overhead that you have to mount and unmount and partition, and that's super clean. You don't have to worry about, does my distributed file system work?
Oh, yeah, but it's not just an SSD with a file system interface. It's a distributed file system across all the SSDs.
Yeah.
It's just,
Sure. Yeah.
Put a 25 gig interface on it, and
No, it's got a PCIe interface on it. On them all.
And it works pretty well.
All you have to do is run NFSD in the main processor.
well, I was just thinking of velcroing them to a wall with cables running them to them.
So this last bullet here doesn't really make sense, right? I'm not talking about the same thing, but it's something I want to highlight. We want to be able to operate in a condition where our storage device can be seen as a fog or edge node, right? Because applications can run locally to the drive, and I'm going to show an interesting application or Scott's going to show an interesting application that's going to make it clear really fast. It's license plate recognition, right?
Oh, sweet.
So we want to make sure that in our software stack, we have everything that enables us to connect our drive to cloud services directly, right? So either you want to move information, that's easy, that's done today, but maybe you just want to, make sure you can run some computation locally, ask the cloud to run computation, pass information back and forth, coordinate, and so on, make the drive a lot more intelligent. That's the future for edge computing.
From an edge computing perspective, I mean, to have your drive be the node, you'd have to have some sort of networking capability in the device outside the SSD.
Yeah. So
and your ARM processors would control that, let's call it TCP/IP stack sitting outside this solution kind of thing.
So the underlying question is, okay, I have an ARM processing subsystem and I have my host. How do they talk? Because this looks like magic, right? These processing subsystems, they need to talk, right? So the problem is that I only have my as a physical connection, I only have my PCI bus, right? And I'm running NVMe on it. So, but every operating system that I know of comes right out of the box talking TCP/IP. Every one of them, right? So we'd say, okay, well, everybody talks TCP/IP. I just need TCP/IP, for low overhead type of communication, control stuff, and so on. Why not use a technology that is more than 20 years old called tunneling, and tunnel my TCP/IP packets through to the PCI bus? And that's what we did. And we get, even now with the FPGA prototype, we get extremely good performance on it. We don't use it to transfer data. We use it to establish the communication between the two operating systems.
So you're doing some
and
sort
that's
of
that's how each drive is now recognized as an IP in the network.
yeah. So you would do some sort of like RPC between the host and the drive in order to transfer control and things of that nature.
Yeah, we can establish an SSH.
Yeah.
That's usually what we do. We log into Linux that's running on the Xeon, right? And then SSH to the drive, and the drive has an IP address, and we manage this. It took a little bit of time to
Magic and all that stuff.
write our agent. It's a host agent that does that communication. It's simple. It just took a little bit of time to think about all the use cases, but it's relatively it's super light.
I mean, the challenge you have is one of, ASIC technology takes lots of money and lots of time to develop. So as Intel and others are advancing PCIe from Gen 3 to Gen 4 to Gen 5, they're starting to get more speed from an interface perspective. And you're sitting here trying to take advantage of processing sitting on the edge to try, so right now you're 4x faster or whatever the right number is, doing processing on the device versus processing in the host. As they speed up, you guys have to correspondingly speed up.
Data is growing much faster than any other technology, right? Data growth, number of zettabytes per year added to, so the amount of drives that you're data centers are acquiring.
The capacity per drive is also growing. So as you're
true.
going to
that is true. That is true. But it's not offsetting, right?
Right.
Not yet.
So it is absolutely true, and we are certainly we are not competing to, let's say, displace the host CPU. As the capacity of each drive are increasing to the point that some of them are 16, 32 terabytes, that no matter how fast is the PCIe lane, transferring this amount of data to make sense out of it, it takes time and energy. And when you have multiple of them, it causes a very fundamental challenge. So it doesn't matter how fast is the host CPU. If you have to move 30 terabytes of the data from each drive, and you have even 40 drives, to move it to the host CPU is not as efficient if it can be done inside the storage.
So, and even without talking like theoretical, we're going for Gen 4, Gen 5, and we don't know how fast it's going to go. We don't know exactly, right? But I can give you an example of something that we're doing now. We're running BLAST, which is an application for protein sequencing, right? And BLAST is interesting because the input files are large and medium and small, and small is large, right? And the large is uber large. And you can control that ahead of time and so on. So what we've shown in many examples is that if you work on scheduling, you can decide smartly about which file is going to be processed locally to the drive, which file is going to be taken on by the different cores in the host, and actually overall increase the performance of the system.
Even if they're all doing the same thing, effectively.
Yes, but they're doing it in parallel.
Yeah, distribute.
And say, this file is too big or too small. It's better if you run it here or there. And that's basically everything that, data flow computing is all about that. And this is getting more and more traction because the problems are becoming super complex, involving a lot of data, right? And you need to take advantage of all the computing resources and not just consider the MIPS available, the memory available, but also where the data is and the cost of moving that data, right? And in some cases, it's worth moving the data. In some cases, it's not. But your point is taken. As the technology will evolve, we're going to have to, fine-tune some parameters. Maybe we have to, add more cores, higher performance cores inside the storage device. Okay, so, and then this actually, so we're not designing an SSD controller, we're not a semiconductor fabless company, right? We design and manufacture SSDs. So we are going to support M.2 and U.2. Obviously, edge card form factor for very high capacity, and the nascent EDSFF that's being pushed by a number of companies, including Lenovo. Scott, you're going to talk more about this later and give more details about what capacities we can achieve and so on and so forth.
So we're getting you really hooked on the tech, and then we're going to show you how we actually deliver it. So
yeah,
got to do it the right way.
So, but the idea is like, okay, super lower capacity, but super high density, small form factor going up to the largest form factor, ultra high capacity, right?